Welcome to the lectures on modern digital communication techniques. So, we have been discussing pulse amplitude modulation. In the previous lecture, we have seen the details of the mapping procedure and why do we call it a symbol mapper. We have also identified that the difference between the levels at the output of the quantizer and the levels at the output of the symbol mapper. So, we should never get confused with these two things. The quantizer output levels are used to choose a bit sequence. These bit sequences are used to re-choose another set of amplitude levels, and the number of amplitude levels you now choose from is quite different and has no relationship to the number of levels at the output of the quantizer. These are completely different things. So, we should never get confused with that. Now, when we talk about choosing the quantizer amplitude levels, the pulse amplitude levels, and that is why we have pulse amplitude modulation. What we are trying to discuss is how to map the bit sequence to the amplitude levels. It is just not a very simple mapping, because we are saying that these waveforms that are getting selected would go into the channel. So, if they go into the channel, it should be able to resist or pass through reliably through the channel. So, of course, there are several ways to improve reliability, and one of the standard techniques is forward error correction codes, and I have always said that this is not going to be discussed in this particular lecture, but we would definitely cover some essential components which are necessary and which are hardly a bit complex, but would add a lot of value to the modulation techniques. So, let us get back to our discussion, and we have identified that suppose we have the pulse amplitude modulation levels. So, let this be 0 and let this be a level minus d, let this level be minus 3d, let this level be d. So, we are trying to follow a dimension which makes sense, and we said that suppose when a 1 1 comes, I would map to the level 3d, when a 1 0 comes, I would map to level this, when a 0 1 comes this, when a 0 0 comes this. So, this is the mapping. So, this is the mapping that you do. Mapping bits to, or symbols, you could say these are symbols to waveforms or bits to symbols, whatever way you want to identify it. So, now we said that suppose we have a waveform, for example, as this. This is an arbitrary waveform example that I am taking and not following the earlier example that we had taken. So, this is purely for the sake of discussion, right. And then we say that noise. So, this is the waveform that goes through the channel, and of course, we have said that there is it is possible to have a carrierless modulation. That means, you could use a carrier and you may not use a carrier. If you are not using a carrier, in that case your signal here Fc is simply 0, and you have Ft equals to root over 2 by Eg times Gt, which is the pulse duration. Simple wave value of Gt could be 1 for the duration of 0 to capital T, and Smt would be Sm times Ft. Ft is this part and Sm remains as this. So, it is not a big deal to think in terms of carrierless, because we have already always said that we are going to discuss in terms of baseband communication, right. So, then we say, if you would recall our earlier discussion, there is source, there is modulator, then there is the channel, and there is this noise getting added before it enters the receiver. And we also said that this noise is because of all kinds of components that are present in the receiver, and one of the simplest channel models that we can think of is the additive wide Gaussian channel noise. So, when we say additive white Gaussian noise, we mean it is additive in nature, right, and we did describe that additivity does not is not a problematic because this noise that gets added, you may not be able to determine and recover the original signal, because this noise is independent of the source symbols. That is what is important to note. And we said it is Gaussian because of the probability density function of noise that we had described in the previous lecture, and we said it is white, and the spectral properties we did discuss, and at that point we have said that you can think of narrow band white stochastic process in the sense that I have a filter which is wide enough to pass my signal, right. This is the filter width, this is the signal bandwidth, if this is f, and this noise also passes through this portion and noise is not passed through this portion. So, in the portion of the signal, whatever noise is present is white, we could say that. So, that is a narrow band and white noise which has Gaussian PDF, and it is white within the band of our concern. Okay. So, getting back, additive white Gaussian noise could produce a time domain waveform which is like this, which is zero mean. We have always said that it is zero mean. That means, if I am sending a voltage, let us say D, then noise of zero mean gets added to that. So, for example, if I send S of t which is zero mean, I am going to add noise to it. It is zero mean. So, therefore, the mean is that of the mean of S t, and if the mean is at level D, that means combined signal will be around level D, right. And here the noise is basically random, right, and so on and so forth. And we also said that there is a decision level, right, there is a decision level and there is a decision level. So, these are decision levels. So, what do we mean by decision levels is that when I receive this signal, so suppose something has been sent, what does the receiver do? Receiver simply observes this, compares it with a threshold, right. If the received signal goes above this threshold, it would say that a plus 3D is the received amplitude, because in this part it has no resolution. If the received signal voltage is below this decision and above this decision, so if it is within this band, you would map it to D. If it is above this, you would map it to 3D. If it is within this band, you would map it to minus D. If it is below this band, you would map to minus 3D, right. So, now if the signal goes above this decision point, it would map to 3D. So, what it means is, if 1 0 was sent and because of the noisiness, it would detect it as 3D, you are going to detect it as 1 1. Similarly, here you have sent minus D, however, it could be detected as plus D or it could be detected as minus D, depending upon whether noise has shifted this level in the upward direction or downward direction beyond the threshold. If noise is restricted to within this level, in that case minus D would be detected as minus D. So, what I am trying to say is that when D is sent, it could be detected as D or 3D or minus D. Now, you could kind of guess from this, we are not going into all details, which we will do at an appropriate time at a later part of the different modules of this lecture. You can guess from these pictures, what I have almost tried to influence to you is that a D can be recognized as a D itself or 3D with certain probability and minus D with a certain probability, right, because and detecting 3D instead of D is the probability that it crosses this threshold, and detecting it as minus D is the probability it crosses this threshold, right, and there is a less probability that it gets detected as minus 3D. Similarly, this one has a more chance of getting detected as D compared to minus 3D, which is even more compared to minus 3D. So, that means 3D getting detected as minus 3D is very less chance. 3D detected at minus D is probably a little bit higher, and 3D getting detected as D is a little bit higher chance. So, all I am trying to tell you is that there is a higher probability of getting detected as a neighboring amplitude compared to further away amplitudes, right. So, this is one philosophy which is used in mapping these bits to the amplitude levels, so that we can get less number of bits going into errors. For example, if we take these particular examples. So, what we have over here is a D getting detected as 3D, you have 1 bit in error. A D getting detected as minus D would also, now a D getting detected as minus D, look at this, this particular is interesting. So, suppose I have noise, right, noise as this. So, this is a decision threshold, this is a decision threshold. So, if D gets detected as minus D, it gets detected as minus D when this threshold is crossed. So, it is 1 0 and it is 0 1. So, a 1 0 gets detected as 0 1. That means, when this symbol goes into error, 2 bits goes into error, right. So, there is a concept known as gray coding. The idea behind gray coding is that you would try to map the particular bits to symbols in such a way that when these changes occur, or this neighboring amplitude levels are mapped by bit sequence in a way that the neighboring bit sequence differ by at most 1 bit. So, what I mean is, if we look at this particular possible options. So, if we see this, we have 0 0 followed by 0 1. So, this and this are the same, only 1 bit difference, but here this becomes a 1, this becomes a 0. So, there are 2 bit difference. So, this does not qualify as gray coding. So, if we take a look at this, again the same thing happens over here, 0 can become a 1, 1 can become a 0 because it is a neighbor, right. All right. Whereas, if I look at this particular sequence, here also you have the same situation, right, a 1 becoming a 0, a 1 becoming a 0. So, we need to find a mechanism by which you could avoid this, and let us try and do that. So, suppose I can just make it horizontal for ease and use better use of space. So, you can have a D, a minus D, 3D. I am only taking 4 levels, all right. So, let us try doing that. Let us put 0 0 into this. Then we need to make 1 bit change. So, let us make 0 1. From minus D to plus D, we can make 1 bit change. So, 0 could remain a 0, this could become a 0. This we already have, so we do not select that option. So, we rather keep of these two 1 which is fixed, and this we change to 1, right. And now we need to make another option, and that option is clear. So, this 1 would remain a 1 and this 1 would become a 0. So, what we see between these two neighbors, this is common, only there is a difference over here, right. Here we see that this and this are common, and there is a difference only between these two, right. And similarly, between this and this, we see that this and this is common, only there is a difference between these two, and 3D and minus 3D are not neighbors, we do not need to worry. 3D and minus D are not neighbors, we do not need to worry. This and this are not immediate neighbors, we do not need to worry. So, let us remap these things. Minus 3D is 0 0, minus D is 0 1. So, here we flip. So, what we do is, instead of this, we make it as 0 0, 0 1. Now, we make 1 1 and 1 0. So, with this new mapping, what we are going to get is that if you are making a mistake here, we take the same example, you have a 1 0 that was sent as D. So, look at this, we are just simply changing the mapping. So, suppose I had sent a D and I detect it as minus D as we took in this example. So, we would have a 1 1, that is 1 1 over here being detected as 0 1. So, this we see differ by only 1 bit. So, whenever you make a error in detecting a particular symbol or an amplitude, at most you would make 1 bit error. That is the philosophy of this particular method of coding, right. So, if we move on further, we can try and take another example, and or you could try it yourself in different forms. We would do it once. So, let us take that you have 8 level PAM. Right. Just a small note at this point, I am discussing gray coding here in pulse amplitude modulation. We will not discuss gray coding in these details as we discuss future modulation techniques. We would assume that you simply extend this philosophy to these other modulations, right. So, moving on to 8 level PAM, this simply implies that you have 8 amplitude levels, that means k is equal to 3 bits. That means Ts, the symbol duration, is 3 times Tb. So, if there is a 0 and this is D, you have 3D, you are going to have 5D. You can do these calculations of finding AM, right. These are the AMs that you are going to get, minus D, minus 3D, minus 5D. We have 6, so you have 7D and minus 7D. So, now you have 1, 2, 3, 4, 5, 6, 7, 8. So, you have 8 levels, right. So, now the problem that is with us, so these are the amplitude levels. The problem with us is you have these bits up to 1 1 1, because they have to be mapped to these amplitude levels, right. So, there could be many solutions. Let us try one. We will begin with 0 0 0, you could then go to 0 0 1, and then we could say 0 1, we have kept these two same, and I have only modified this. Then you could have a 0, a 1, a 0, that means you have modified only this bit. So, between this and this we have modified only this bit, and then we could have a 1 in the middle, a 0 on the right, a 1 over here, that means we have modified only this bit, right. Further moving down, we could say 1 1 and 1, that means you are modifying this bit. Then we could say 1 1 and 0, make this, and then you could have 1 0 0, you modified this bit. So, in this way what we see that these two neighbors differ only by 1 bit, this and this neighbor differ only by 1 bit in the middle bit, this and this differ only in the extreme right bit, this and this in the extreme left bit, and so on and so forth. So, by this way, if I am sending level D and by mistake I go to level 3D, that means this is my decision point, these are my decision boundaries. Right. If these are my decision boundaries, then the neighbors, that means if I am sending minus D and detecting as D, you are actually sending 3 bits per amplitude levels. So, whenever you make a mistake, at most you are going to make at most 1 bit error between neighboring levels, right. So, that is what we have achieved. You could try for yourself as an example or as an exercise that can you find some other mapping instead of the one that we have displayed over here, and could you write a short algorithm or a script by which you could automatically assign these bit sequences to the levels in a gray coding format. So, you can try out an exercise where you can develop a MATLAB code. Let us take MATLAB, right. You could use Scilab, which is a freeware, you could use Octave, you could use C or C++ or Java, whatever you feel like, so that you write a small program of your own by which you would take bit sequences and then you would map these bit sequences to amplitude levels, right. So, what I am trying to hint to you at this point is you should start your activity from now on a particular programming language through which you should be able to simulate the performance of a communication system in future. And since we have started the communication part here through the digital modulation, this is appropriate time to start it. And of course, you could have done similar things for source coding, but we could assume that there is a source of bits which may have come through a compressor or may not. But now we are at the stage where we are actually sending these bits into the channel. So, therefore, this is a very crucial part that we are into, and I would highly recommend that you would start using some software where you could develop this as the first algorithm in the domain of digital communications. All right. So, with this we move forward, that hope we have understood some of the basic concepts of gray coding, and at this point we are also interested in writing or calculating the Euclidean distance between any pair. These things would be important when we start discussing error probabilities. We have already given indications of how an error can happen. We will do details of calculating the probability of getting into an error. That means, if you send an amplitude D, what is the chance that you would detect it as some other symbol, and the moment you detect it as some other symbol, it is an error. So, overall we will try to calculate on an average what is the chance of making a mistake. So, that is going to happen at a later time, but when we do that, whatever we are writing now would turn out to be very, very handy. So, D m n e, that is what the notation that we write, Euclidean distance between the level m and level n. So, we define it as Sm is the symbol coefficient minus Sn. So, this you can think of vector notations squared, and Sm we have already described how we should write Sm, that is we have it here, right. So, from this you could calculate this as root over Eg upon 2 times mod of Am minus An, which would turn out to be d square root of 2 Eg into modulus of m minus n, right. So, this would be useful, and for m and n being neighbors, that means if you would say that I want to calculate the minimum distance, which is minimum. So, m and n would differ by at most a value of 1. So, you would get d root 2 Eg, that means the minimum Euclidean distance between the two neighbors, that is the closest, right. This is between any two, m and n could be any two amplitude levels. Further, at this point I would also like to point out that the carrier modulated PAM that you have is basically a double sideband. That is very clear, because you have AM GT cos 2 pi FCT. So, if you look at the spectrum, it will be double sideband, right. And what we could do is, instead of sending double sideband, you could send a single sideband, because it is spectrally more efficient, and in that case the Sm of t could be written as real part of AM GT plus or minus j g hat of t, where g hat would be the Hilbert transform e to the power of j 2 pi f c t. So, this is how it would look like, and this is of course the Hilbert transform of g t. And you could, we have already said that if you are talking about baseband transmission, then we would write Sm of t is equal to AM GT, and that is also clear from here, because Fc is 0, cos 2 pi FCT is 1. So, we have Sm, which is this multiplied by this portion. So, this and this cancels out, you have AM times GT. So, we already have seen this expression. So, this is not very different, and we have also described how does the signal look like. So, still we can draw a representative picture of the particular waveform that we have with us. So, if for example, we have a waveform, let us say which is of this shape, right. So, if it is baseband, it is just this particular envelope, and if it is with carrier modulation, I need to redraw this picture. So, if it is with carrier, and you are going to get, sorry, I made a mistake here, this will go up till here, and here there will be a phase reversal, and after the phase reversal you are going to get this. So, this is with carrier, this is in baseband, and generally this looks like the amplitude modulation. However, you have these discrete levels that we have already discussed, and the special case when you have m is equal to 2, we have already discussed this, and so we should be careful over here. We have said that A1 is equal to minus t and A2 is equal to plus t. So, I just need to give a reminder at this point. So, if you look at these two levels, what you would also encounter is phase shift keying, which we will study later. So, this is also known as binary phase shift keying, because you have two signals, and the difference between these two signals is this phase, which is 180 degrees. There is a minus in front of it. So, in other words, you could also look at this particular signal, and you could say that there is a plus theta, there is a 2 pi FCT plus theta, and theta is 0 at one point and theta is pi at another point. And if it is so, that means FC would be 0, but you are going to get AM gt cos of theta, and am is constant in that case, which is d, only theta changes. So, just briefly let me write down, you are going to get am, or rather I would write d times gt cos 2 pi f c t plus theta m. So, if f c is equal to 0, you would get d times gt cos theta m, and theta m could take a 0 or pi, and if this is equal to 1, for 0 you are going to get a d, for pi you are going to get a minus d. So, which is same as this. So, which you are going to encounter at some later stage. So, all I want to point out here is, although we have discussed PAM at a very special case where m is equal to 2, the PAM would look very similar to a binary phase shift keying, which we will start discussing in the upcoming lectures. Thank you.